Hidden within the intricate biochemistry of vitamin B12 lies a quietly unfolding story, one that involves a molecule called homocysteine and a puzzle that bridges cardiovascular disease, cognitive decline, and even accelerated aging. While folate often receives the spotlight in discussions of homocysteine regulation, vitamin B12 is an equally critical, yet frequently overlooked, cofactor in this process. Without sufficient B12, homocysteine levels can climb silently, without outward symptoms, until damage manifests in the form of arterial stiffness, memory loss, or neurological impairment. The true significance of this interaction lies not just in the presence of a single amino acid, but in how subtly and persistently B12 deficiency can distort metabolic balance long before classic signs appear. Homocysteine is a sulfur-containing amino acid that arises during the metabolism of methionine, an essential amino acid found in dietary protein. In healthy individuals, homocysteine is either remethylated back into methionine or converted into cysteine via two separate pathways. Vitamin B12 is indispensable for the former. It acts as a cofactor for methionine synthase, the enzyme that converts homocysteine into methionine using a methyl group donated by folate. When B12 levels are inadequate, this conversion slows dramatically and homocysteine begins to accumulate in the blood. The result is not just a disrupted methylation cycle, but a gradual rise in a metabolite known to be toxic at elevated levels. This silent accumulation of homocysteine is a biochemical red flag, one that has been repeatedly linked in epidemiological studies to increased risk of cardiovascular disease. Elevated homocysteine can damage endothelial cells lining the arteries, promote oxidative stress, and enhance the clotting potential of blood, all of which contribute to atherosclerosis and thrombotic events. Yet for many individuals, the cause of this imbalance is not a genetic mutation or dietary excess, but a simple, long-standing B12 insufficiency that goes unnoticed and untreated. The vascular system, which depends on finely tuned methylation and nitric oxide signaling, may become progressively compromised under this quiet pressure. Perhaps even more compelling is the role of elevated homocysteine in cognitive health. Homocysteine is neurotoxic at high concentrations. It interferes with neuronal signaling, promotes excitotoxicity, and may even accelerate brain atrophy, particularly in regions responsible for memory and executive function. Several large cohort studies have found that elevated homocysteine is associated with a significantly increased risk of Alzheimer's disease, vascular dementia, and general cognitive decline. In some studies, brain shrinkage correlated more strongly with homocysteine levels than with age. Once again, B12 enters the picture not as a peripheral nutrient, but as a central modulator of neuroprotection through its homocysteine-lowering function. What makes this even more clinically relevant is that homocysteine can rise in the absence of anemia or other textbook signs of B12 deficiency. This metabolic B12 deficiency is especially common in older adults, vegetarians, and people with absorption issues, yet it remains underdiagnosed because serum B12 levels may still fall within the normal range. Functional markers such as methylmalonic acid, MMA, and homocysteine provide a more accurate picture of intracellular B12 status, but they are not routinely measured in standard blood work. As a result, many people with persistently elevated homocysteine may never be identified as needing B12, even when that intervention could significantly lower their cardiovascular and cognitive risk. The implications of this are both sobering and hopeful. On one hand, a failure to address subclinical B12 deficiency may allow homocysteine-driven damage to accumulate for years. On the other, this damage is not inevitable. Homocysteine levels respond rapidly and reliably to nutritional therapy. Supplementation with vitamin B12, alongside folate and vitamin B6, which support related pathways, has been shown to lower homocysteine levels in numerous clinical trials. In some studies, this reduction in homocysteine has been associated with slower cognitive decline and fewer brain volume losses in high-risk populations. While not all studies show definitive cognitive or cardiac outcome benefits, the biochemical logic is sound, and the risk-benefit ratio of B12 supplementation is extremely favorable. Methylcobalamin, the active form of B12, may be particularly useful for supporting methylation and neurological function. It bypasses several metabolic steps and may be better utilized in individuals with impaired B12 transport or conversion. For those with elevated homocysteine, high-dose B12, often in conjunction with folate and B6, can form a cornerstone of targeted nutritional therapy, potentially staving off years of silent vascular or neurological wear. The homocysteine puzzle, then, is less about a single molecule and more about the silent consequences of modern nutritional imbalances. It reveals how even mild, chronic B12 insufficiency can act as a long fuse, one that doesn't just spark anemia or neuropathy, but erodes vascular and cognitive health over decades. By recognizing B12 not just as a blood vitamin but as a methylation cornerstone and homocysteine regulator, we uncover a layer of prevention that is biochemical, actionable, and surprisingly underutilized. Vitamin B12, quietly ensuring that homocysteine stays in check, may ultimately be a key player in extending health span and safeguarding the brain and heart from the subtle toll of time.